You know, your talk will be also transmitted by YouTube because we are incorporating the talks in my lab YouTube channel. Is it okay for you?
Of course, otherwise people cannot see it, right? That's good. The more you can share, the better.
Okay, thank you so much. We have to wait some minutes for the students to come in.
Sure, sure.
So how is the weather? You are now in?
I'm now in Germany, in Göttingen, actually. Göttingen here is in the center of Germany, pretty much. So this summer it's not very hot. We have something like 20 degrees and it's raining today. So it's not as nice as I can see you're sitting outside, right?
Yeah, well, in fact, this is it's not an outside. It's kind of, but it's a co-working space. I am in a seminar of my institution, the Ministry of Education and Culture, and now I am in the outside of the rooms, but it's inside of the building. But it's kind of if it is like a street.
But that's
so
cool.
It looks like it's a co-working space. It's very nice. Yeah, it is really nice. Yeah.
And you have good internet there. That's important.
Yeah. This is important. Yes, of course. So.
I called the devil, right? By saying she had good internet. Apparently that was the moment when she was disconnected.
I think she has traveled.
I shouldn't have said that. Never say that the internet works well.
I'm sorry that I made a mistake.
I just said I shouldn't have said that your internet is well, right?
No, it wasn't the internet, it was me. Made a mistake. Okay. Well, now students are, now it's also Carolina Pereira is also co-organizer of the course.
Hi.
Let's wait a little bit. We usually take, let's say, 5 minutes to wait the students to come in. We have a quite widespread distribution of students from different parts of Latin America. So it is very interesting, the interchange also with the students, and in some way, as we already did a similar activity last year, we're kind of making or contributing to make a network of people in the region, trying to promote the use of do-it-yourself, and it's open source tools for science and for teaching.
No, but that's really cool. That's really nice. I was only stumbling into this Lego microscope. I really was just basically playing with my son, and then I had to give a class for students in school about my research. And it was obvious that I could not bring in any kind of real microscope. And then I was wondering what we can do. And then I was really playing with my son Lego. And then we had this idea, and I thought it will not be possible, but we were just playing. And then in the end, here it is. That's what it is. It's actually fun to play. It's not complicated, right? So it's pretty robust. And if you have someone who likes Lego, then they will be. It's not hard to build. It's really quick.
That's great.
But this network you're mentioning is all over Latin America then?
Well, in fact, there are many groups in different parts, in different countries, in Argentina, in Brazil, in Peru, that I know are kind of promoting in Chile this open source movement. That is, you know, the GOSH, the global open source.
Mm-hmm.
And there are also kind of nodes in the region, and so it's kind of moving towards promoting collaboration and also improving teaching with low cost technology.
Yeah. I mean, this is really good because you can do a lot actually, even with very simple things. I mean, for microscope, I think the fold scope is awesome.
Yeah. Yes. Also, we had also we had also a talk from Jim from fold scope.
Yeah.
And Paula. Yeah. So.
I mean, here the idea is to kind of like excite kids, you know, and for the kids, the fold scope is already a little bit too hard because everything is small. It's not so easy for them. But I mean, the quality is so good. It's very impressive, really.
Okay. Well, I don't know. Maybe we should start. Yeah. So, yes, because if not, then we will have a shorter time at the end. So I'm going to introduce you, and then the student may come in the next minute. So, well, this morning is very nice for me to introduce you to Timo Betts. Timo Betts got his master in arts and physics in the University of Texas in Austin, United States, and then a diploma in physics in the University of Würzburg. I don't know if it is well spelled.
Hard to spell. Würzburg.
Würzburg, Germany.
One of these mean German words.
Yeah. And then he got a PhD in science at University of Leipzig, also in Germany, and an habilitation title in physics at Université Pierre et Marie Curie in France. So he also had positions in all these places, and now Timo is professor of biophysics at the Third Physical Institute in University of Göttingen in Germany. And he his research interests are mainly related, as far as I realized because of the publications, to the membrane and the forces, physical forces that different kind of molecules involved in the physical forces of the membrane of the cell. Recently, it was in other topics, but also it's related to the physics of different biological processes. So it is very nice to have his contribution to this school with this Lego-based microscope with a very relative high resolution that Timo will show us. So thank you, Timo, so much for accepting the invitation, and the floor is yours.
Thank you for the invitation. I have to admit, this is the first talk I give actually on this microscope. As you said, normally I'm doing more science-related things on cell migration, cell mechanics. I actually started even in neuroscience. I was interested in neuronal growth cones in the beginning and how they generate forces, how they move forward. But then I was more getting into fundamental biophysics. And as I already mentioned, this whole project here, this designing a Lego-based microscope, and we then added here for an educational setting, came to our mind when I was literally playing Lego with my son, actually already a couple of years ago. And at that time, I had to make a presentation about my work to school kids at the age to like 12 years old. And it was possible to motivate many of the things we do, but it would have been nice to also show them something with a microscope at the time. And the research microscopes we have in the lab are, of course, way too bulky and also too expensive. You don't want to put them in the hand of these kids just running around there. And then we thought about, or I asked basically my son if he thinks we can build a microscope on our own. And he was totally into it. And then we started building it. And I have to admit that it was really quite fast. Within a week, we had something like what you see here, the first prototypes, and later we had to work a lot, of course, on the resolution. So he's also co-author here, Emil Beetz-Bläser, this Emil guy, that's my son. And Bart Voss was later, or is a postdoc who helped me to really bring this in a state where we can publish it. So the whole idea why we wanted to push that then out, besides just having fun with this, with my son or in the local area, was really to see if we can really excite children more about science. And science is really, I think, or children are very interested in their environment. They want to learn, and they're very motivated actually already to learn something. And sometimes the problem is that we don't really get through to them. So we don't really access them, because especially as being a scientist who normally works with students that are already at the age of adults, sometimes it's hard to get this across. And it turns out that when you start playing in this playful way, you get a quite good connection. But why should we actually get kids excited about science? And I think it's really nice because we can help them develop very important skills, for example, communication. Because when you start really thinking about science, discussing this also with your classmates at this age, you start training your logical thinking, but also to communicate. Try this, try that. This is not easy, and it's really, these communication skills are highly relevant nowadays, and also I think in every day, not only in science. Also, this to remain organized, especially for kids. But if I would show you my desk, also maybe for me, this being organized in your head, right? This is something that is very important. And when you kind of like try to care about scientific problems or scientific questions, or if you want to build something like this here, like this microscope, you need to be organized. And I think this is also something that's important for the kids. To stay focused, this is also, I don't know, some of you might have kids. This is one of the things that's really hard for many. And when you can excite them about something, they will stay focused. Also, develop critical thinking. This, I think, generally why we should try to make kids excited about science, so that they really develop their own opinion and that they think about how things might be or might be not. And this comes immediately in this like famously infamous term of alternative facts, you know, so that really already at the age of kids, young ages, kids should start to understand what facts are and what it means and how you can test, how you can kind of like learn about this. Okay, so the approach that I tried to push here was really this idea to connect learning with fun. Because very often in school nowadays, the idea of learning is not necessarily connected to fun, because you have to sit and all of this. And I realized quite quickly that at least in a certain age, Lego itself, Lego as a toy has an amazing power. Like kids are very creative about this, and they really like just playing. They can be focused for hours. They can talk about it. So really the idea was maybe we can get this. And since I'm developing myself a lot of microscopes, the idea was here, and as I already mentioned, partly also for this course I gave there, was to find out, can we not try to combine science and this Lego? So this idea of having bricks, simple bricks that can construct also complex situations. And the idea was really, can we do this? Can we get a microscope that has sufficient quality that it's really usable from Lego parts, with the aim that the kids can not only use it to look at their environment, look at, I don't know, the wing of a bee or something like this, but also to learn about optics, to learn about how optical components are working. And in the real microscope, most researchers that I know that are not physicists, they don't really know the details of a microscope. And here you have something where you can basically play with it. And that means you can very easily also change parts and you can figure out how things work. And this was really the aim. Now comes the problem, right? Because if you start with this, you immediately have to ask yourself some questions. If you look at a microscope like standard microscope that you get from the internet, one of these images, you see there are many, many components. And there are some components that might be easier to build in Lego. For example, a stable stand, you know, that's nice. With the Lego bricks, we can really build a stand. But we also need to make sure that distances are optimized. That's already maybe not so easy, but here the flexibility of Lego really helps us. But then already the next point is starting to get into trouble, and that is we need really good position accuracy. So Lego in itself Lego parts are nice, of course, but you already know, whoever had played with it, it's not precisely aligned, right? So you can put stuff in or out and everything can move. And we need to go, when we want to have high accuracy or also high resolution, we need to go down in position accuracy in the order of 0.1 millimeter, right? 100 micrometer. That's the diameter of the hair. That's really something we have to see how we can solve it, but it's possible actually. The next thing is also difficult in Lego. It's generating light. Right? So what we have here is normally a light source, and Lego is normally not made for light. I just say like burning is not an option, right? But nowadays the good thing is there are already some very flexible Lego parts, and we even could find a way to create the light source by Lego. And then comes slowly the optics. The ocular, for example, is the first part, let's say the first loop you see, or the first lens you see when you look through a microscope. And that is, normally just a lens. And this is really difficult in Lego. I was actually trying, there are some Lego loops. You can really buy them, a little loop, but the quality was really not sufficient. So this was one part where we definitely had to weasel out. I come later how we solved that. I'll show you this later. But this part, yes, but all the rest, the housing is possible. And then, of course, the hardest part was this objective, or the objective revolver here also. And obviously, in a microscope, image quality depends very, very much on high-end optics. And here was also one of the things where I was a little bit in trouble, because I didn't want to build something that where we need to use really objectives from real microscopes, because I wanted that parents play with their kids doing this, and this is something that we will not get there. So I found a way out, and I will show you about this later. So these are basically the main problems that we have to solve. And before I show you how we solve them, I mean, this is what you do when you make some scientific advance. First, you go to the literature and you try to see what have other people done. So what is the state of the art here? And there was actually already a proposal for a Lego microscope, and this is really beautiful. That was functional in the sense that it used actually these Lego loops even. However, the problem here was that also it's very beautiful. I mean, I really don't want to make this in any case bad, but the problem is that it's really hard to build this one. And there are also many non-Lego parts involved in here. That makes it really kind of special. Then there is something that was really called a Lego microscope, or the Lego scope, that was kind of like developed by Harrison Liu and colleagues in California. And you can already see that's also close to a design that we will later see for me, but it still has requirement of 3D printed parts. And you can see it in here, maybe here, kind of like there is still some real microscope objectives as you would buy them or have them in a high-end objective microscope. And that's why we need here these 3D printed parts. So this is, again, something that is a big hurdle for parents at home. So this is nothing that you would just simply do because a 3D printer, most people don't have at home. And also buying such a lens, even so it's not super expensive, it's still something like 50 to 100 euros. And then there's, of course, the fold scope we were talking about. This is really a beautiful design. It has amazing capabilities. However, it loses a little bit on this play part. So this is really something for kids. This is really already very good for adults to observe things, or maybe even for labs to look at. But this is not so much useful for kids because many of the parts are fine to adjust. And if you have some like rough hands, this fold scope might be not the right thing. One thing that I also realized that it uses a ball lens, and that turns out to have quite some spherical aberration. So what I was trying to do, I was trying to get the best out of each of these worlds to make our microscope. And I even tried the ball lens from the fold scope, but here again, I had the feeling that for the kids, it would be a little bit too hard to align this. All right, there's also something else that I found. I was really impressed. There is something super fancy. A group in Barcelona actually generated a light sheet microscope, fully automated, that really works. But of course, this is kind of like then losing this idea of having it simple to build for the kids, right? But there is really quite something out there, and there's really very impressive stuff. So what the pro and cons are of the microscopes that are already out there. So this beautiful design here is, of course, visually attractive and has great design, but it's already too complex to build for kids. And the image quality that you get there is quite low. So it's even a little bit, I don't want to say frustrating, but it's not really useful to study optics, in a sense, if you want to learn about optics. Then there was this Lego scope. As I said, this is also very simple design, so it's very suitable for kids. It also has very high imaging quality, but it still requires these high-end optics, and it still requires 3D printed parts. And that's, again, something that you cannot just hand somebody over a plan. That is something where people really need to invest a bit more, also especially having a 3D print. And then there's, of course, the fold scope, as I said already, high quality and amazing design, but it has just not this toy factor. That's a little bit missing. So that's why we actually went on and we spent some time, and we had then here our Lego microscope. And here's a little movie that I will show you that I did yesterday. So this is the microscope. Here we have the building instructions. Can turn it around, and we will talk quickly here about the different parts. And then I will have an extra part. I will disassemble each of these. So this up here will be the ocular, and it's just in a housing. We'll talk about this in a second. These here are simple extensions. We can make them shorter, longer, depending on what kind of extenders you use. And that's important for changing the distance between the ocular and the objective, which will actually influence the magnification. And then we have in here kind of like the core part, which is the objective drive. So we can just unmount this very easily. So this here is the objective drive. And in here we have at the moment already sitting one objective. That's basically one lens. And there are two objectives currently, but in principle, there is no reason not to have more. So this part we will also assemble and reassemble in a second. So this is really important because what we have here is this kind of snail drive that later allows us to very carefully, very precisely adjust the focus, because we need to adjust the focus in the order of a couple of micrometers. This here is then the main body here, which is also nothing than just pure Lego parts. This can also be easily dismounted here. And then we come down to actually the housing of the lamp. If I open this up here now, you can see that the lamp housing has two main parts, which are here, this rather sturdy mounting for the sample later. And the key part is actually this here, which is the lamp. And as you can see, I can go closer here. I have here already the white light. There's an extra video explaining how we can change the LEDs. You cannot buy it with the white light LED. And down here, it's just a very simple mechanism that basically pushes here on the lamp. Yeah, so this is the main kind of like disassembling or assembly, or here I disassembled these different parts. And what I would do in the next few minutes, I basically show you some videos describing each of these parts individually, so that you, if you're interested, if you have questions here, you can really immediately jump in and I can say more or less. But yeah, these things I thought I'd prepare a little bit in advance. So we start with the most, let's say, easiest part to solve, and that was actually this light source here. And you can really just buy such a brick. And one of the problems is, I mean, I just like here have a little zoom in it. In the normal light source or light brick that you buy, the LEDs are not strong enough. So you can see something with these LEDs, but only if your sample is yeah, transparent most of the time. And that's why actually we have a way to, or we just have a little video to show you how to change the LED. And this is basically that little video. All you need is, you need just a screwdriver. You can buy these LEDs, standard LEDs for 40 cents, something like that, in any electronics shop. And if I just run that video here, all you have to do is basically, you have to open up with a little screwdriver here, this light brick. This is, by the way, the same procedure when you want to change batteries. They're just in there. You can see it's a super simple mechanism where you have a LED sitting in there, touching the two lenses, touching the two batteries. And then on the back, there is a connector. And that connector then helps you to turn the light on. So you just have to unmantle here all of this, get the LED out, take a white LED. As I said, you buy these in any shop. You just have to bend a little bit these connectors here so that it fits in. This is very easy. You just look at the LED you unmount, you just bind it in the same way, and then you can fit it back in. And you close everything, and that's it. As I said, you can the same way also change the batteries. When you change the battery, you have to be a bit careful before you unmount the battery. You have to look where is plus and minus, because it's not written on there, of course. And if you do this the wrong way, it doesn't work. But there are only 4 different possibilities. So if it really doesn't work, you can just play. And here we have then the lamp with white light. So this is one of the parts that is important, this lamp. But as I said, it's not really hard to then the next part would actually be here, the objective holder. And that was, I think, the most complex part to build, I would say. And it's also when the feedback we get from children. So for children that are below the age of 10, it's better not to let them build this part because they get frustrated. So if you have kids that are good in Lego, age of 10, it's fine. They manage. But this would be an advice if you want to do this, try to help them with this part and let them build other parts on their own, because they don't like this. But I show you here how to do it. Or the next part would actually be part of the Lego microscope, or the important parts. Actually, this objective holder. So we have a little wheel here on the top, and when we turn it, we can very nicely move and very carefully move here this slider. Later, the objective will be mounted here so that we can actually move and focus. This part is, I think, among the hardest to build, and there are several catches. So what I will do now is I will disassemble it so that you can see it, and then we will reassemble it so that I can hopefully show you where the trouble is. I will do the reassembling according to the plan so that you hopefully feel familiar with it. So these 2 parts basically are later just necessary to mount the objective. What we have here are this rail system. Basically, if we dismount that, where we have this rails here, these little ripples are necessary for the sliding. If you look at the side, these are the ripples. And it's all kind of held in place here by that rail system. Just mount that. Then all of this is basically driven by that worm drive. Just dismount that also here. We have the legs. One part can be like fixing this. Then we have here this side part that's fixing all of this together. This side. Dismount that so later we can quickly reassemble it. And then here, of course, that's just the wheel that we use for driving. These little guys are basically just there for holding everything in place later. Right? They just fix us here. They just fix. Okay, we'll just get rid of this guy here too. And here's the hardest, probably among the hardest parts, which is getting this warm drive right. And I will show in a second where the trouble comes from, because we have here this fourfold symmetry of this kind of like block, and we can use these warm drives at different positions, but we need to make sure that later the warm drive is really kind of like smoothly going. Okay, let's disassemble that further. Okay, now it will fall apart if I move this and that part. Now you see actually, I remove this and this how it's falling apart. So what we have here are 3 of these little warm drives. And if I connect them later here, you see there is, it's closer. There's this point where it actually starts to overlap. And this can be in different positions. There are 4 different positions, right? This is kind of like the worst situation where they really don't align. This here is starting to get better, but there is a little gap in it. This here would be the right position. You can basically see from the side also nicely, you can see this, that all the distances are the same, so there's no jump. This one is not perfect, but it would be maybe even accepted. The simple thing is really to take a look close here at this part. I don't think that my camera is able to catch that close here. And that should be smooth. And now there is a little gap. So we go back to the right. Here it's all smooth. Okay. So I cut out the part of the reassembling just because it would take in the end too much time. But this is really the hard part if you want to make sure later that you need to find here the right thing. Otherwise, you will later realize that it doesn't move very well. Okay, so again, this, if I would build that with somebody that, or with a kid that's a little bit younger, that's better if the adult does it, but many of the other parts can be built by the kids. Then comes here the ocular. And here I realize actually that the sound is not working. So I will just talk about it. So really the ocular part is basically here a little housing which fixes more or less one lens. And what we used there was a very simple plastic lens that we got out of for €2 out of an astronomy a shop who does simple astronomy parts. Here, the idea is just that the ocular then goes on top of these extenders, and the extenders are necessary to have the right distance between the ocular later and the objective. Why did I use the extenders? It's very simple. This Lego, I didn't have enough Lego bricks, right? You could also, of course, make Lego bricks and make this higher. Another thing that's nice about the extenders is that you can change them. So when you disassemble this part of the ocular now, you will see that there's just a very simple mechanism that in the end holds here this plastic lens in place. If you want to play with this, we can also use different lenses there, of course. It would be like in your, if you've ever used a real microscope, you sometimes have oculars that are 10x or 15x. So depending what kind of lens you use there, you can really have later differences in this ocular. And here you see on the left, there is another lens housing, which basically has another lens, and then this needs to be adjusted by the distance from the eye to this ocular lens. So this is what I mean. This is parts, these things you will realize very quickly when you build this. Even kids realize this when they change the lens. It doesn't work anymore. You can inspect it. You can see, you look through, suddenly you see it again. So, oh, the distance is wrong. And these are really things that are very nice to explore. And even for adults, as I said, like mostly everybody knows from school how a microscope works, but you typically have no chance to play with these things, right? And what we have here, these lenses are yeah, they're so cheap that one of them was not good enough. So all we did, we just added 2 of the lenses, and then you had something that had a higher or a shorter focal distance. When you have a kid that's already more into math, you can even start here talking about how that works, how you can calculate the lenses. Yeah, so this is just fixed in there. It's a little bit loose, but it doesn't matter in the end of the day. It's just like it has a little bit of a play, but there's no problem. And as I said, this is again a part that is even for the small kids normally easy to build. It's a little bit more complicated, but it's not really hard. So I mean, a 9-year-old, 8-year-old will have no trouble in building this part. Okay, so then if we go through, we have now the light, we have this objective holder, we have the ocular. Obviously, what we need next is kind of like the objectives themselves. And here I have different objectives kind of like generated. The simple one that I will show you here are the ones where you have large macroscopic lenses, and then there's another one that will come in a second, where we have then this iPhone lens that actually then allows you to really have also high magnification. But there should be some sound to this. Let me try that. Now we come to these objectives, or yeah, these are two different kinds. In principle, it's very simple. All we have here is a little cage, right? That does nothing than actually fixing a little lens that's in there. So to prove that there is a lens, let me just use that as a magnifying glass here on something. Hopefully that works. So here you can see that's a nice magnifying glass, and that could just be one of the objectives. So this is the simple objective, which has only magnification that later will allow us to see larger samples. The high magnification actually uses then the iPhone lens, and I will later show you how to dismantle and how to mount that. Both of them are very simple. We have here 2 different lenses. This one, you can maybe see it already in the video here. The lens is a bit thicker than that one. The main difference is that here we use, sorry, okay, so one is thicker than the other. Here we have another lens with a higher quality. This is a so-called, it's hard for me to show that. So this lens has a higher quality because it is a duplex lens. That means there are 2 lenses coupled together. So this one will not generate so much spherical aberration. This one is a simple lens that you can get from Edmund Scientific. It's easier to get. But it will have some optical artifacts there a little bit. I mean, you might see them later when we show you the differences. Just very quickly, both of them are mounted the same way. We have down here, we have them connected by such a little device. It's always the same that we have here. Basically, just some very simple mounts. Right. Put this upside down also. And in the end of the day, the lens is simply clamped here between these round parts. So this is simply one of the lenses. It's clamped here. This is fixed top and bottom. So here we'll have fixing it like this, right? This is the top part, and the bottom part is fixed here. Same over here. Okay, I will stop here because we run out of time otherwise, and it's just remounting the same thing. And then there comes the high resolution part, and that was really something that took some time. So as I said in the beginning, I was inspired by the full scope, and I was trying to actually use a very small ball lens to get this into one of the Lego microscope parts. That was really, really tricky. And I realized that kids will not be able to handle that, because the ball is really just 1 millimeter, that it will be dropped and then it will be gone, and then they will not be happy. Also, the ball lens, it's amazing how good it works. It has, of course, this very strong spherical aberration on the edges. And again, that's something where I had the feeling that the kids might be not so happy with. So I was playing around a little bit with different solutions. And what I found was really just using here this iPhone camera module. So really you can get, I mean, they charge amounts that are very high for the iPhone, right? But when you have a replacement part of an older generation, this was $2, something like that, or $3. So you can get it very often on eBay, very cheap. It's a bit of a shame because what I do is I dismantle, I dismount everything, and everything that's kind of high class technology, I will destroy, right? For example, here, this is the chip. And all we care about is here basically this little part. But the lenses, the plastic lenses that are in there are really amazing. Why are they so good? Well, they really made them in a certain shape and with a certain material that has hardly any chromatic aberration. And also these are aspheric lenses. That means they have hardly any spherical aberration in all of this. And I think they must produce probably millions of these, and then they test them for the quality because it's really good. In the end of the day, this is a little bit a hack if you want, you know, how to mount this. But the best thing that we realized was really just basically putting here a cover slip and just clamping it with a cover slip and putting this on scotch. I have also made a little movie here, but I think I will actually skip this because we don't have time. And it's just basically showing you very quickly here how this is mounted. I mean, I can later put this online on the GitHub page. And here it's trying to help you a little bit how you, I just run through this very quickly, how you dismount this, because that is something that's not so easy. But in the end of the day, it's not hard. You just have to play around a bit. Also something that the kids should not do, of course, because you really need. Now we want to see, let me just go on. Okay, and that's basically it. That's then the Lego microscope if you want. And just as a little fun thing here, I made a little stop-go video to mount it. And that's really just created here at home. So when you know what you do, it takes something like 20 minutes, maybe less to do this. And that's already one of the samples. This would be here an example of just normal onion, red onion, doing an osmotic shock. I will show this later again. Okay, so that would be the kind of like talking about the microscope. Now I would start showing you some images, and I would start talking a little bit how we go towards the kids. If you have questions for the microscope, it would be a good moment now. Okay, otherwise you can also ask them later. Okay, so these are just, I will go through that quite quickly. You remember we had two kind of objectives. One is the low magnification, that's something like 25x here. This here on the left would be a fish scale. What I have here is just head region of a honeybee. You see like stuff that's in the order of 1 millimeter. You can nicely see these regions here. That would be something like a diameter of a hair, right? But you can already very nicely see this. This objective is the cheap one, and it has spherical aberration. You don't see it here so strong, but maybe you see it here more. This here on the left would be just a leaf of, I think it's a bee, of normal beans. Yeah, it's a normal beans plant. And you can see here towards the edges, it's not sharp anymore. And that's really the spherical aberration that we have. In the central part, it works quite well. Below here, I was actually getting some neurons. So I was looking around for some neurons. These are some motor neurons that were just very simply stained. Great. And these are large cells, of course, but you can see that here, you can, even with this very low magnification, you can quite nicely see here these neurites, these extensions. And if we now go to the higher magnification, which is something like 220x, by the way, this is the total magnification. It's not kind of the objective as we used to, it's objective times ocular, right? So you can see here very nicely, actually, the structure of the stomata. You can very nicely see here the structure of the leaf. That's just the same sample as on the left here. And down there, these are then these motor neurons. And I must say, I'm quite happy. So this is really very nice. You can really see here motor neurons. You can see different neurites. And I will talk about the resolution in a second.
Yeah, this is great.
Yeah, these are just some samples I could organize. Yeah.
Fantastic.
It's actually nowadays hard. Everything is of course stained for fluorescence microscopy. Yeah. So it was a little bit harder. But yeah, I found something. Yeah, that's just a little bit. I really like this, I have to admit, because this is really pretty cool. This is really the details of a stomata. So there you can really, with the kid, talk about. I mean, it looks like a mosaic. It's beautiful, and then you can really discuss how cells regulate water, and this is also the entry point for diseases of the cells and all of this. And You can see this is 10 micrometers. So this here has in diameter something like 50 microns already, or here the slit opening something like 10 here. And you can really see this quite nice. Then just some fun stuff. So this would be just like these Artemia. We also do zebrafish, and this is what we feed them. And that's actually, this is real time what you see here. So they really just swim in there. And when I give this to kids, I normally give them some of these eggs that you just put in salt water, and about 1 day later, you already, they hatch and you have this. Another thing that kids can normally prepare, we made a little movie for this, is really this osmotic shock for the onion cells. And that's quite impressive because all you do is this again, almost real, no, it's not real time. So you see the time up there. But you can see very nicely how you actually have here, because of the high osmotic osmolarity at the outside, how the water leaves the cell and boom, and now you have this transition. And then you add pure water again, and then they come back. So this is something that I must say is quite impressive. And they can really see this with a higher magnification lens. So yeah, by the way, this on the left here would be low magnification, that here would be high magnification. And then I also tried to get something out of some water ponds that we had here. This is the paramecium. So it's a little bit, yeah, when you do this at home, it's a little bit, I don't want to say disgusting, but you have to put, they feed bacteria. So it smells not very nice when you grow them, but it's kind of fun because they can really, you can watch them swimming around. And what you can see here also is already that the plastic lens after some time gets scratches. So this comes actually from, not from the objective, but this comes from the ocular because it was falling down a bit. That's one of the downsides of the plastic lens. The advantage is it cannot break very simply. Okay, so let's quickly go a little bit about optical performance here. So what we did is, since it was not standardized, we really had to calculate the magnification the old way. So really just took an image with something like here, you know, this is 5 millimeters of a normal sheet of paper. So this is something that kids can do. Below here, they can't do that anymore. That would be one of these standardized gratings where you know the distance at each of these stripes. But using this, we could then actually calculate on one side and measure here the magnification, and that works quite well. So theoretically, it's 27x for the low magnification. Sorry, theoretically it's 23 and we measure 27. And for the high magnification, theoretically it's 220 and we measure 250. One question, we have now 45. Is it okay if I overdo a bit in time or? Yeah, okay, good.
Yes, so, please, this is okay, it's okay.
Okay, good. Then I will just try to hurry up, but yeah, I would like to show this. And then we tried to really see what is, because we wanted to publish a paper on that, you know, I'm still a scientist and we were trying to really go to the limits. So we really tried to measure actually the resolution, and we really did this by having these standardized lines. Here, this would be then the high magnification objective here, the low magnification objective. You can already see the low magnification, also it's low, the quality is less good. And the reason is just that these lenses are simple. These are simple lenses, whereas on the left, we really have this iPhone lens. And it's quite impressive here, right? You would imagine that the low magnification has better quality.
Sorry, the difference is in the materials? It's a crystal for the iPhone and plastic for the low, or is it?
It's the other way around, actually. We have glass for the low magnification. I just bought simple glass. And in the iPhone, they use plastic. So the iPhone lenses are made of plastic. Yes. But the reason is that I think they have a mold and that they can very simply generate it by having the plastic polymerizing into these molds. And I think they really generate thousands of these and they just measure the performance. That's my guess. Because when you try to do this on your own, generating a lens from a mold, very often they're not perfect. And yeah, but that's my guess. I don't know how they make them. But so to measure this, all we did is basically we're taking here just a cross section. And then you see here these intensity profiles. And then what you can do to define something like a resolution is basically you take here a function like a sigmoid function, and then you look at the sigmoid function. You can also do the derivative, then it's a Gaussian, but you do here, you try to find out where is the turning point and when does it actually level off. And that gives you an idea about the resolution. And in theory, that's actually quite interesting because in theory, the resolution, we measured the numerical aperture also, of the high magnification would be like 500 nanometers. So it's really amazing. And we measured like 780 nanometers. So we could really here on the left images, as you can see here, this is 4-6 micrometer distance, and we could really very nicely see here how the signal goes down. So we were with the iPhone less amazingly close to the theoretical limit that we calculated. On the other hand, on this glass lens that the cheap lens or the low magnification, you can see like in theory with the numerical aperture, it could be about 1 micrometer, but we could not get there. And you see this on the image already. And the reason is the image, the quality of these lenses. These are just cheap glass lenses. But yeah, but you can work quite well. I mean, I showed you these images. So the last couple of seconds or minutes, I would like to spend what we did now around that to kind of like access the kids, because you cannot just give them the parts and the plan in the hand and expect them to learn something. So what we generated was something that we called the Discovery Kit. So basically it's instruction of something like 10 pages or 20 pages, where step by step they get a little thing. They should try to solve a little problem. And then by that, we guide them actually through the way of building it. And they will start with just the ocular or just playing around with the light source and something like that. So that's really step by step. And it's also the little text. And we translated that also, of course, German, Dutch, and also Spanish. I thought that might be interesting to you. So we have a Spanish translation.
Great, thank you.
And it's in, yeah, and just what it does normally, what we did, we always asked the kids first to do a little test. And this test was done in a way that we had 10 questions. And of these questions, we had 5 that were related to optics or to the microscope, and 5 that were just normal or other questions. And then later we could see how they perform before and afterwards. And this, the normal questions were basically our control, right? So that you see that that shouldn't change. And it's just very simple, just for example, here, very general questions, but then suddenly there's already something about color. And then here it's like how the microscope works. But so one thing that's important that most people are not aware of, that when you look through a microscope, that everything is inverted. So this is, for example, something that they almost always know. First, they don't know that the P changes, and afterwards they understand that the P is inverted. So yeah, this is something you can do, but you don't have to, but it's also included. This is nice if you do this in a class context somewhat. And just very quickly, what are now these parts of this discovery kit? So the first thing what we ask them is to build 3 main parts of the microscope. So basically, but they don't connect them yet. So they build the ocular part, they build the housing for the lamp, and they try to build actually this slider for the objective. And then they should play with it. They should try to figure out what it is. Again, normally the way it was done, that the kids didn't even know that in the end it will be a microscope, right? So we were just asking to play around. Normally what they realize is they realize quite quickly that the ocular is like working like a loop. It really works like a loop, and they start playing with this. And then comes a very quick problem for them, because when you want to get too close, then the housing makes it dark. So you can't see anymore. So that's then the next thing, right? Focus on the ocular. So we really tell them, look at this. In case some kids didn't realize it's a loop, you know, we kind of push them. And then we say, like, what is the problem? And that is the problem. You cannot see something when you want to get too close. And then, but you can use actually the light, right? Because then they can put the ocular on top of the light, and then they can look at whatever they want already. This is kind of nice, and they can figure that out on their own. They can play with it. So that's cute, actually. That's, when you watch that, that's nice. And then they can start looking at samples, because they have built something like a better loop, if you want, because they have their own light source there. And then normally we would ask them to sit back a moment and write a little bit down what they have figured out so far. That's also a little bit for the parents to kind of like, or for a class kind of moment, if you want to do this in class, where you can say, like, now we all carry everything together. We try to assemble information. And then we ask, can we now get better magnification? How can we get better magnification? And what they realize already is that the distances for a loop matter, right? So the further you go away with the loop, the higher is the magnification. And this is something that they can already learn here. Another thing that they, of course, also realize when they want to increase the magnification, they say, oh, maybe we use 2 loops, right? Or a better lens. So these are things that they learn. And then you actually start introducing the objectives, which is actually a better lens already. And then you can start, again, interrupt to collect experiences. Then they will see, okay, this is like with this high magnification lens, it's a little bit harder because everything is so close, because the focal length is high. And then the idea is that they can combine the parts. So really the idea is that they try to come up to use one loop to look at the other loop. And this is basically what a microscope is, right? You have two lenses, two loops, and you look at one and try to look at the other. And they are able to do this. So if you give them something like a rough surface, like a text or something, but it's very hard to align it by hand. It's really, really hard. And then you can immediately come to the point, okay, now that is cool, we can get this, but it's almost impossible to keep it in focus and keep it aligned and all of this. And then comes the last thing where you basically just say, well, combine this and make a microscope out of it so everything is together. And then you have this point 11 where you start looking at samples. And that's actually really nice because they can build up, they realize distances, and all of this. Yeah, and then you can introduce the high magnification objective for looking even closer. And yeah, in the end, then you can expect like really these very challenging micrometer sized samples. And if you do this with the kids, this is then what we figured out. They really learned. So this is really just, as you see, we have a low number here. Why do we have a low number? The problem was we wanted to bring this in a school last year in May. This was how it was assigned. And that's just when COVID happened. And then we were waiting and waiting. And at some point we decided we made little sets and hand that out to individual kids. It was not as nice because we couldn't help them, but at least they were doing this on their own. And then we had this test. But you can see very nicely that the general questions, they answered equally well before and after playing with the microscope. But here, the microscope related questions, they were really improved a lot. So you can see some of the questions are very simple if you look at them, so many already realized. There were some that were really smart, but afterwards, most of them really gained a lot of additional information. So that worked nice. And that is really something where I'm quite happy with. So we can really show that the kids learn. And then we put all of this on GitHub. So if you want, you can really get all the parts there. You can also change things in a way. So if you have an improvement, for example, if the Spanish translation is not good, you can make suggestions and then we can add this. If you're not known, if you don't know Git so well, I mean, you can, when you go here to code, you can also download it as a zip file. So this would be kind of like the plans, you can just download them as PDF. And then there's also this paper that we just then made out of that, which gives you many of the details about this. So this is also open access paper in the Biophysicist. That's a new journal about education in biophysics. And that's it. Sorry that I took longer. Very important, of course, acknowledgements. So as I said, this is half of my group. So this other guy here is Aris Russ, and we were in Münster in the same institute. So half of these people are somewhat connected to me. And very important is here, of course, Bart Voss he's also here in this crowd. He was really the person who in the end was measuring the resolution, and he was kind of like doing the theory and comparing it. So all of these things were really thanks to him, and he also wrote most of the manuscript. And then, of course, big thanks actually to this guy here. As you see him in action, that's my son. When we played here with this was really the very first version. You see, it's not all one color, but it's nice. And yeah, Emil, thanks to him, because without him, this would never have happened. And thanks to you for staying with me a little bit longer. And I'm very happy to take any questions.
Thank you very much, Timo. It was a great talk. I really enjoyed it a lot. And I'm very enthusiastic about the possibility of promoting the use of your idea, your creative idea with this microscope for the primary and secondary kids in Uruguay. I was invited by the foundation, Ceibal Foundation, to try to teach kids for using Foldscope. That I've been introducing this Foldscope here, but now I will add also your microscope, and it would be very nice because you also have the Spanish instructions. So the first question would be if there is any, because there are many possibilities of Lego toys, boxes. Is there any one that is more suitable for this kind of I mean, because you have
Yeah.
some pieces that are maybe it's not so often in many. So
Yeah, no,
maybe you
absolutely.
can suggest which Lego should we buy?
Yeah. So what I would do is we provide here something. If you go to the GitHub page or if you download this whole as a zip file, there is something that we have here, just plans and parts. And there's an XML file. It's a file that is called, I think, LDR for Lego Draw. And that file you can upload to a link that is called Bricklink. So there's a web page called Bricklink, and what that gives you a possibility to say, I would like to have these parts.
That's great.
Give me someone who sells these. And then you will see on the whole planet, there are so many, I don't know, there are thousands of people selling individual Lego parts. And you will actually get, based on your location, you will get one reseller that is close by.
Oh, that's
and
great.
it's very simple. You just go to this Bricklink, you type in you set up an account, and then there is something like a wish list, and then you can drag and drop that file in there, and then it will actually tell you which.
That's great.
If you have trouble, sometimes it says like, oh, we can't get all of the parts. Very often that's because of the color, right? So it could be that, but we had to assign one color. Of course, the color doesn't matter.
Yeah, of course.
So don't worry about this. But yeah, and if you have trouble with this, if there are some parts that are not there, you can write me a mail. And then very often there are also other parts that are very similar. But yeah.
Yeah, I see that it is, at least, even if I didn't touch it, but it looks more stable. I mean, very stable. And also these two things that are important here is that you reach more magnification. 220, is it?
220, yes.
Yeah,
that was.
it is quite a lot. And also you take care of the circular aberration. That is a very limiting fact in the foldscope. I mean, both things. Yeah. So I mean, it is a very good improvement compared to the other. I mean, each one has its own maybe space, because maybe with the foldscope you go to the countryside or to the beach.
Exactly.
Yes. And it is very good, but maybe for indoors it's better, and you have many advantages. So thank you so much. It's great.
I mean, really, I think I want to really emphasize the main advantage really when you do this is that you realize how a microscope works.
Yeah,
in the moment where you
this
have the two lenses and you do this and you try to align it, then you realize, but it's so hard to align, and then but just fix it. And that is something that
it makes me remember at a course in Marine Biological Laboratory in Woods Hole, we play with the lenses, and it is similar to this, but more sophisticated lenses.
Yeah.
we put in a line, and we play with lenses and with the lights and all this stuff. So it was kind of the same thing, but for older people.
No, but I agree. But that you don't want to use expensive optics for when you have a 10-year-old kid who then suddenly wants to watch a comic or like a cartoon and then comes back.
And do you think it would be possible to make a fluorescence?
Yeah, so I tried this. So I was looking into these LEDs. You can also get in other colors. And you can kind of see something. The problem that I really had was I couldn't get filters, tubes that are affordable, right? Because this is really something I was trying a lot of different filters. Like there are some good filters for cameras already, but very often they take out too much light already. So for, I don't know, certain color filters for cameras, but normally they operate at daylight. And then you have several things. You have the problem that the LED is not so strong. And on the other hand, the filter is not so good. And then I could hardly see anything. Yeah.
Okay.
But I have to admit that I then stopped. I think there is possibility, because there are very strong LEDs now. Very powerful LEDs.
Yeah.
And I think if you would try one of these powerful LEDs, it might be possible.
Yeah, and
but my main worry was the Actually, in the beginning, I was trying to build an optical tweezer even. So I had a little laser that was coming from the side and was going down.
Optical tweezer, wow.
An optical tweezer, yeah, because I'm building optical tweezers.
Yeah.
And that was close to working, but then I realized that the laser power I would need is just too dangerous for kids.
Too
because
dangerous
if they
for
really
kids,
at that
yeah.
laser power, it's just a couple of milliwatts, like 5 milliwatts, but already this,
It's too much.
if they would start looking at it.
Yeah, the retina, you will feel
Yeah. And then I said, okay, that's not worth it.
no, it's not safe.
Yeah, it's
Okay.
not a good idea.
Well, the students, do you have any questions? I was so...
En español si queréis. Hablo
Oh,
un poco
great.
español.
Bueno, buenísimo.
Pero con un acento alemán.
Pero se te escucha perfecto el español.
No sé. Si tengo que hablar un poco más complicado, no sé si va a funcionar. Y normalmente no estoy discutiendo la ciencia, pero...
Pero hablas muy bien. Bueno, gente, ¿alguna pregunta, algún comentario?
Ahora la excuse de la lengua.
No hay excusa por el idioma.
Eso es.
Bueno,
Bueno, pasa
una
nada.
pena que no tengan preguntas para hacer, pero
No,
a
pero
ver,
está bien.
pregunta acá, Sandra, ¿en qué países ha sido ya divulgado? Have you shared knowledge on this microscope in any other countries?
Well, I mean, we really have only so far published the paper. We have then
It's quite
translated
recent,
this.
your paper.
It was
this year.
It was in April or May.
Yeah.
And that's basically it so far.
So we are very...
You're early.
lucky.
You're the first talk that I gave on this. Yeah.
Yeah,
This
this
why
is
I had-
great, and I acknowledge you very much. It was very nice
I had to
to
make
have
these
you.
movies. So
Yeah, that's great. That's great. Thank you so much. It is very. We are privileged. It's a privilege for us to
But
have
if
you
you, for
here.
example, want to translate to another language, really do it. This is all open. It's really open source. It's like GitHub. You can
Yeah.
send me a pull request. You can put this on your side. You do whatever you want. You're happy. You send me a pull request, and I can integrate it here. And
That's great.
It's really.
It's very generous of you.
Yeah. No, I mean, this is the only way how it works.
Yeah.
To
This
be
is
used.
Okay, so well, thank you so much, Timo. We'll keep in contact.
Okay, so if you
I
need
will.
help,
Yeah, I will try to do it here in Uruguay, and then I'll show you.
if you have trouble, really don't hesitate to write me, because
Okay.
sometimes there might be things. It's also for me interesting because there might be things that are hard to do and I don't even realize because
Yeah, because
I made the plan. Yeah.
Yeah, of course.
So
okay, and
totally...
are you thinking in any other kind of scientific instrument? Maybe you have something in mind?
Yeah, what I wanted to do first, I wanted to see if I can introduce fluorescence here, right?
I'm sorry?
Fluorescence microscopy.
Oh, yeah.
This is
why
really
I asked
something
you.
that I have in mind. And then, to be honest, like more complicated things it's a little bit against the idea. So at some point, it would be that I'm doing it only for myself or for other biophysicists, and then I think I'm not sure, because I realized that there are many cool Lego things out there, but they're very much for adults, to be honest.
Yeah. I see.
And then you lose a little bit the idea is to be simple, and the idea is that the kids can really have fun with it and play with it. And if it drops, it doesn't matter.
Yeah, that's great.
Yeah.
It's so that they can play and they can learn by playing. Yeah. This is great.
Yeah, exactly. That's the idea.
Oh, that's wonderful. Well, thank you so much, Timo. It was a great morning.
Perfect. Thanks a lot. And then I just have to hedge over for my next meeting, actually.
Okay. Thank you.
Ciao.
Bye. Bye. Bueno, gente, nos vemos la semana que viene. Pidieron algunos de los grupos para reunirse el lunes en la tarde. Y después les quería recordar que tenemos la presentación de Juan Lerma, editor de Neuroscience, que va a estar el jueves que viene también. Así que les pediría por favor que estén. No grabamos nada. Ay, pero fue por
¿Grabaste?
YouTube.
Ah, está en YouTube. Ah, sí.
Está en YouTube, menos mal que está en YouTube.
Sí.
¿Está? Ahora estoy viendo, no grabé por Zoom, pero por suerte la vi estaba retransmitiendo
Sí,
por
cuando
YouTube.
entras te avisa que se está grabando. Yo por eso me quedé tranquila.
Claro, yo
Pero
también.
vi en YouTube.
Está,
No me di cuenta que
bueno,
no era en Zoom.
está.
Pero bien.
Bueno,
Bueno,
así
estamos en
que
contacto.
nos vemos.
Nos vemos.
Anden bien.
Chao,
Chao,
chao.
chao.
Gracias. Bye.